So let's put all the pieces of our integrated rate laws together. We've talked about integrated rate laws for first order, zero order, and second order reactions. So what do we actually do with this when we're faced with a problem? So what you're going to do is basically follow 4 steps. And so the first thing you're going to do is actually collect concentration versus time data for a reaction. And it's important when you're doing this that only one chemical has its concentration substantially changing throughout that reaction. So you can really focus in on what is the order of a reaction with respect to one of those chemicals. Everything else you're going to want to have enough of an excess of so that their concentrations don't change. So that's the first thing. And then once you have done that, what you're going to do is actually collect that data and make 3 graphs. And you're going to see which one is the most linear. If when you graph concentration versus time, that's the most linear, you're going to have a zero order reaction. And so you can write your rate law is rate equals K times the concentration of A to the 0. If natural log of A versus time is the most linear, it's a first order reaction. And if 1 over concentration versus time is the most linear, it's a second order reaction. So you're just going to look and see what is the most linear. At that point in time, you're ready to actually write your explicit rate law. So you know what your exponent is going to be for that particular chemical, and you happen to know what the value for K is, because remember, you can figure out what your rate constant is from the slope of your line, from that most linear line. So you have all the pieces to write your explicit rate law. And then lastly, once you have an explicit rate law, you can use the integrated rate equation to calculate concentration, half-life, time, etc. If it's a zero order reaction, use the zero order equation and so on. But you have a value for K, and so you can use those integrated rate equations in order to solve the problems. So let's pull this all together by looking at one final example. So let's take a look at a reaction where the chemical C4H8, that's butene, is reacting to form 2 C2H4 molecules, and that is ethene. And so we have some time versus pressure data, and for kinetics data, you can use pressure as a proxy for concentration, because our equations are for concentration, but concentration is about the number of particles per volume. Well, pressure is about the number of particles in a particular volume because of the number of collisions that are resulting from those particles. So they can be used interchangeably. So let's take this data. We're going to find the order, then come up with an explicit rate law, and then figure out how long it would take for the pressure to change all the way down to 50 millimeters of mercury. So the first thing you're going to do with this is you're going to take that data and you're going to create 3 graphs. And so you're going to graph the concentration, or in this case, the pressure of our chemical with respect to time. And you're going to make a second graph that is the natural log of the pressure with respect to time. And a third that is 1 over pressure with respect to time. And let's make this look a little bit prettier over there. Okay, so you're going to make these 3 graphs. When I took this data and graphed it, pressure versus time, not linear. So this is not a zero order reaction. Not zero order. Natural log of pressure versus time, that was looking pretty good. That was looking pretty linear. But I graphed the third one just to confirm it, and as I had kind of thought, we had a definite curve. So it's not zero order, not second order, but it is, because it's the most linear, a first order reaction. And so now I know what order the reaction is. And when I did this graphing, I found the slope of this line. And the slope of this line was found to be negative 1.9 times 10 to the negative 4th. So that's my slope. And so we can use this information to figure out our rate constant. Okay, so I've identified, taken my data, I've identified that it's first order. And so now what we're going to do is write an explicit rate law for this reaction. So I know that my rate is going to be equal to my value for K, which is the opposite of the slope. So in this case is 1.9 times 10 to the negative 4th. And since it's first order, my units are inverse seconds, times the pressure, in this case, of C4H8, raised to the first power, because it's a first order reaction. So there's my explicit rate law. And then the last thing I was asked here is to figure out how long would it take for the pressure to be 50 millimeters of mercury. Okay, so let's do this. So I know that I need to use my integrated rate equation, and since it's a first order reaction, this integrated rate equation is that the natural log of the concentration at some time is equal to minus kT plus the natural log of the initial concentration. So with that in hand, let's plug our values in and see how long it takes. So the natural log of the concentration I want, which is 50 millimeters of mercury because I'm working in pressure, so the natural log of 50 is equal to minus 1.9 times 10 to the negative fourth inverse seconds times T, which is what I'm solving for, plus the natural log of the initial concentration, or in this case pressure, which was 400 millimeters of mercury. And so once I have that, it's just a matter of plugging in these values. And so you're going to take the natural log of 50 and get a value for that. And I'm actually going to solve this one all the way out. This was 3.91 is equal to negative 1.9 times 10 to the negative fourth inverse seconds times the time plus 5.99. You're going to collect terms, so you're going to get the numbers, the values that don't have time in them onto the same side. So negative 2.08 is equal to negative 1.9 times 10 to the negative fourth inverse seconds. And then solving for, almost missed it, times T, solving for time, I get 11,000 seconds. So 11,000 seconds is going to be needed to have a pressure of 50 millimeters of mercury.